Hello everybody, my name is Gautam. My final project is called SimHUD, a real-time heads-up display simulator inspired by the helmet-mounted display systems used in modern combat aircraft like the Apache helicopter. The idea was to build something that actually works the real way HMDs, helmet-mounted displays, work, using nothing but two consumer webcams and open-source computer vision tools. In the Boeing Apache attack helicopter, the pilot wears a helmet with a transparent visor. Instrument data, your horizon line, your heading, your altitude, your airspeed, is drawn on that visor. There's a targeting reticle that slaves to wherever the pilot is looking. That's the inspiration. That's pretty cool, isn't it? Uh, so now we not all of us can be lucky enough to fly an attack helicopter such as the Apache, right? But the child in all of us wants to experience that feeling at least once. So the central design decision is the dual camera architecture. So the camera sits on a cap on my forehead at this position here, right here, and that's the worldview, the canvas where everything gets drawn on. The other camera is my laptop camera watching my face from 40 to 50 centimeters away. These two cameras never need to see the same thing at the same time. The face camera handles all the math, head pose, wing detection, and the results drive what gets drawn on the world camera feed. This is exactly how real HMDs work. The display layer and the sensing layer are separate. For head tracking, I use MediaPipe face mesh, which gives me 478 landmarks in real time on a standard webcam. I pick 6 of them: nose tip, chin, eye corners, mouth corners, that correspond to the known 3D positions on a canonical face model. I feed these into OpenCV's Solve PNP, which solves the perspective and point problem to give me the camera to face rotation matrix. From there, I extract the Euler angles, pitch, yaw, and roll. Pitch drives the horizon up and down, roll tilts it. These angles also feed a simplified flight dynamics model that updates airspeed, altitude, g-force in real time just to get the feel of a real pilot. One thing worth noting is below about minus 10 degrees pitch, Solve PNP becomes unstable because the chin landmarks start getting occluded. I handle this with a rejection filter. If the roll angle jumps to minus 179 degrees, I know it's a flip and I discard that frame. Gesture control uses the eye aspect ratio from Sokupova and Czech's 2016 paper. EAR is a single number, the ratio of the eye's vertical opening to its horizontal width. Computed from 6 landmarks, when it drops below 0.2 for 2 consecutive frames, the eye is closed. I compute EAR independently for each eye. A wink is only registered when the dominant eye closes and the non-dominant eye stays open. That distinction is crucial. Otherwise, a normal blink would trigger our so-called missiles. A single wink cycles through the targets. 2 winks within 1.5 seconds triggers Fox 2, the firing event. In testing this, I faced a few difficulties. It was not as accurate, and at times I needed to blink multiple times in order to trigger it. I built 2 targeting modes. Mode A uses the Harris corners, and so every 15 frames I run a Harris detector on the world camera, pick the 5 strongest corners, and after non-maxima suppression, show them as green circles on the HUD. Single wink cycles double, and double wink fires. This is great for static scenes. Model B, however, is for tracking moving objects. This is where things get interesting and fun, like a person walking across the frame or an aircraft flying across your field of view. When you press T, I switch to a dynamic tracker. The Mach 2 background subtraction finds blobs that are moving. But here's the problem. If my head is moving, the Mach 2 thinks everything in the scene is moving. So I built a stability gate. I monitor frame to frame changes in pitch, yaw, and roll. Once all three are below 1.5 degrees per frame for 8 consecutive frames, I consider the head stable and I start showing candidate boxes. Once you lock by pressing the key L, CSRT takes over as the primary tracker with Lucas Canade optical flow running in parallel as a secondary. Every 10 frames, I verify the box against a stored HSV histogram and a ORB descriptor signature. If the appearance score drops below 0.35, the tracker declares the target lost. And we need to lock onto a target again. Here, this is mode A. Note that I have just fired a missile and it has hit the target. The target is here. The other Harris corners are shown by these green circles, and the ones that we have locked onto is shown by this red reticle. Notice here there is pitch, yaw, and roll displayed here, and then there's our heading, then there's a bank angle displayed here along with certain flight details such as speed, altitude, and the G meter that's also displayed here. Let's moving on to mode B. This is an object that was moving. My friend here was had volunteered to do this, and we will see this in the demo too. So let's watch a video demonstration of this system. Here I'm just starting up my program. So this is what it looks like. This is the feed in the bottom right from my FaceTime camera, from my inbuilt FaceTime camera in my MacBook Pro, and the larger image is from the camera that I was wearing on top of my head. So as you can see, I am demonstrating how, by moving my head, the FaceTime camera, the feed through the FaceTime camera is being analyzed in order to detect my pitch, as in how whether I'm looking up or down, and to what degree am I looking up or down. And this, what is being tracked, is called the pitch, which determines how much am I tilting my head either to the left or right. These values, in addition to being reflected here on the screen, the green line basically denotes the horizon, and the small bore sight aircraft image here displays the bank with respect to the horizon, and here I'm demonstrating a yaw movement, which means turning your head to the left and right, and these values are also being being printed or being overlaid on the screen in the bottom right corner. The a make-believe heading is also being displayed here, and accurate bank angles are actually being displayed at the top here by this small triangle. As I tilt my head to the left and right, it moves along this semicircle. Notice how I'm cycling through the Harris corners. The green dots are the ones that are being detected, and I'm cycling through a single wink, and double wink is causing is making the missiles fire. As you see, Fox 2 is being displayed and a splash is displayed on the locked on Harris corner. This is the static target detection. Now we'll move on to the more fun part, that is the dynamic object tracking. I will be trying to track this box, and here I'm trying to lock on to the object, and now yes, I've successfully locked on. And now, as you see, even when the object is moving, or even if my head is moving, I can still successfully track this object. Even though the confidence in the tracking varies, which is denoted by the change in the box color, you notice that it's being tracked fairly well, and despite my head moving. So this was something that was fun playing with. Even here, a double wink will cause a missile to fire, and as you saw, the missile was fired with the Fox 2 being displayed at the top and a splash being displayed on the target. that brings me to the end of the demo. I hope you had fun watching that, watching the video demonstration. To summarize, the dual camera was the right call. It made everything else tractable. Head pose estimation is accurate and low latency in the normal operating range. Wing control works reliably when you're deliberate about it. The consensus tracker is a meaningful improvement over either algorithm alone. The main limitations are all related to the single camera constraint. Yaw past 40 degrees, head motion confusing Mach 2, and rapid movement triggering false wings. The natural next step is IMU diffusion, IMU fusion. A phone gyroscope as a secondary pose source would fix the yaw problem entirely. An ego motion compensation in the background subtractor would let the dynamic tracker work even when the head is panning. The demo video shows the system running live. We saw the Harris mode, we saw the dynamic tracking, and the firing animation, all on actual hardware that we as students possess. And with this, I come to the end of my presentation. Thank you so much.